Hello everyone, welcome to Winkle's class once again. Today's video is about intramolecular aldol reaction, and just like the normal intermolecular aldol reaction, which usually occurs between two molecules like a ketone and a ketone, an aldehyde and an aldehyde, or a ketone and another aldehyde, this kind of reaction, which is the intramolecular one, occurs within one molecule. Okay, it is the same molecule that has two functional groups within it. All right, so it could be one molecule having two ketone groups, it could be one molecule having two aldehyde groups, or it could be one molecule having one aldehyde and one ketone group. All right, and a specific example is what I have on the board. This is what we refer to as a dicarbonyl. A dicarbonyl because it has two carbonyl functional groups, a ketone. It has two ketone functional groups in them. Here could be an aldehyde, or both of them could be aldehydes, and it is still going to undergo intramolecular aldol reaction. So for us, it's a dicarbonyl. We are going to go with that. All right. So before we dive much more into this content, I would like to remind you that you shouldn't forget to subscribe to the channel if you are new. And also don't forget to like the video, share with your friends, and comment on it if possible. And don't also forget to turn on the notification bell so that anytime I release a video, you'll be the first person to get notified. Alright, thank you very much. Now let's look at what we have today. Just like aldol reactions, okay, there is a condition under which they usually occur. And for the purpose of this video and this course specifically, we are going to be using a basic condition, right? So we are going to use a base for this particular reaction. The base is going to serve as a catalyst, all right, for this reaction, okay? And for the reactants that we are going to use, obviously, as I said earlier on, we are going to be dealing with what? Dicarbonyls, okay? So a specific example is the one on the board. This is a diketone because it has what, two ketone groups in there. Alright, now let's look at how the mechanism actually occurs. What details do we have in the mechanism? Alright, don't forget, try as much as possible to pay full attention. Alright, if you're able to follow me right now from the beginning as I've started, okay, to the end, trust me, your understanding or your level of understanding of aldol reactions will definitely increase, because this video is meant to give you the step-by-step guide, okay, throughout the mechanism. Alright, so as I said earlier on, we are going to be using a base. Alright, so I will decide to, you can choose any base of your choice, but then a suitable base that I usually use is sodium hydroxide. Alright, so I'm going to use sodium hydroxide as my base, okay, for this reaction. And before you start any kind of mechanism in terms of intramolecular aldol reactions, the first thing that you need to look at is your molecule. Check the status of your molecule. Check to see if your molecule is symmetrical or not. Alright? When we talk about symmetrical molecules, they are molecules that are easily divisible into two equal halves, okay, where one part can serve as the mirror image of the other. That is what we call symmetrical molecules. Alright? So if a molecule is symmetrical, then it should be divisible into two equal halves. Okay? Now look at this molecule. We want to check if it is actually symmetrical. You would realize that if I count 1, 2, 3, 4, 5, 6, 7, I have 7 carbons in this system. Is that not it? And if you look at the first ketone system, everything that is attached to this ketone system, okay, is also present in this ketone system. So it looks like everything that is here is the same thing that is here, okay? So if I decide to break this molecule, okay, if I divide it using this plane in the middle like this, you realize that whatever I have here is same as whatever that I have here. Do you get? Good. So if you have a molecule that looks like this, it tells you that it is symmetrical. Do you get it? If I have, let's say, let me just make some small or slight change to this system. If I have a substituent here and another substituent here, this is also a symmetrical system. Okay, but then if I have a substituent here and I have a substituent here and here, then this ceases to be what? A symmetrical system. Do you understand? Good. Now I'm going to focus on the first molecule, alright? Which is this. So this is a symmetrical system. Now the next thing that you also have to do is to check, okay, check to see if this molecule can be able to form carbanions or enolate ions, because the basic unit that you are going to need in order to allow this particular reaction process to occur is what? Your enolate ion. If you don't have the enolate ion, or if your molecule cannot form an enolate ion, then it means that the reaction cannot proceed. Okay, now we need to find out how we can form an enolate ion or a carbanion throughout this system. Okay, and from my previous videos, if you watch the video that I did on intermolecular aldol reactions, you understand perfectly how carbanions are formed. Okay, don't worry, I'm going to put the link to this particular video in the description section. Okay, so that anytime you feel like watching, you can just follow the link and then watch it. Okay, and then get understanding from there before you come back to this particular content. All right. Now we want to find out if our molecule is capable of forming carbanions, right? And now we know carbanions are usually formed by what? Taking alpha protons, right? So you need to be able to find out if your molecule contains alpha protons, right? Now follow me. Let's check. There are two carbonyl systems here, which means that we would have more than what? One alpha carbon in the system, all right? Now we say that alpha carbons are carbons that are directly bonded to the carbonyl carbon, okay? Now if you take this carbonyl system, the carbon that is bearing the oxygen is what we call the carbonyl carbon, all right? And then the carbon that is directly bonded to that carbonyl carbon is what we call the alpha carbon, right? And for that matter, any hydrogen that is attached to that alpha carbon is what? An alpha hydrogen, and that is what is going to help us to form our carbanion or our enolate ion, right? So now it means that we have an alpha system here. This is also an alpha system, why? Because it is directly bonded to the carbonyl carbon, right? When you come to the second carbonyl system too, this is an alpha system. This is also an alpha system, right? So you can see that we have alpha carbon 1, alpha carbon 2, alpha carbon 3, and alpha carbon 4. Okay. Now, because I said this particular, because we agreed that this particular system is a symmetrical one, okay, it is obvious here that we can say that alpha carbon 1 is equal to what? Alpha carbon 4, and alpha carbon 2 is also equal to alpha carbon 3, right? So it means that whatever you do, whatever operation that you do, or whatever operation that happens on alpha carbon 1, if you do it on alpha carbon 4, it's just the same repetition. So you just have to focus on one of them. It's either you work with alpha carbon 1 or alpha carbon 2. Okay. Then when you come to, it's either you work with alpha carbon 1 or alpha carbon 4. Okay. Now when you come to the second aspect, which is alpha carbon 2 and 3, it's the same thing because they are equal. Alright, because they are equal, whatever you do here, it's just going to be the same thing that will happen here because what they are symmetrical. Right? Good. Yeah, so another thing that you also have to focus on, okay, is that you need to bear it in mind that intramolecular aldol reactions always result in the formation of what? Cyclic products. Okay, so bear it in mind that at the end of your reaction, you are supposed to get what? A ring structure, a cyclic end product. Okay, it could be a triangle, it could be a square, it could be a 5-membered ring, 6-membered ring, 7-membered ring, 8, 9, 10, blah 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 blah. But everything depends on your starting material. Okay, just bear it in mind that you are supposed to what? End up having what? An end product that is what? In a cyclic form. All right, good. Now that we have established our symmetrical system, we know the status of our alpha carbons. We also know the products that we are expected to form. Now let's see how we are going to go about the transformation. All right. Now, as I said, whatever you do on alpha carbon 1 is the same as what will happen on 4, and whatever you do on 2 is the same as what will happen on 3. All right. So here, because we have 2 instead of 4, because of symmetry, we have 2 carbonyl systems in here. You understand the reason I'm saying that, right? Because of symmetry, instead of 4 alpha systems, we are going to focus on just 2, because whatever we do here will be the same as whatever will happen here. Okay, so we are going to end up getting 2 products. Keep this in mind. Okay, the number of possible carbanions that you can form determines the number of final products you will get when you are dealing with these intramolecular aldol reactions. Okay, so because I have gotten 4 alpha positions, which will potentially give me 4 carbanions, okay, I will end up having 4 different products, of which, because of symmetry, okay, 2 of them will be similar. Do you get it? So whatever product that I'm going to get if I work with this one will be the same as whatever product that I'll get if I work with this. The same thing. Whatever product that I'll get when I work with this will be the same as whatever product I'm going to get when I work with this one. Do you get it? Yeah. So now just keep it in mind that we are going to be having 2 products at the end of our reaction, right? So now let's focus on. I want to use this position as my first carbanion position. Alright? Now, the first thing that you also need to think about is what? The base. What is the function of the base? Why is the base in there? The base is there to help us what? Form the carbanion. It helps in the abstraction of what? A proton. Okay? And that is what is going to help us form the carbanion. Alright? So, if I dissociate this base, okay, if I dissociate this base into its components, I would have a sodium ion and then a hydroxyl ion, right? Now, my alpha carbon has hydrogens on them. Is that not it? Good. Now, if my base comes here, the hydroxyl aspect of it is the base that I'm going to use. Okay, so I'm using this as my base. Okay. Now, what happens? The base abstracts the proton, and then the proton donates its electron or brings its electron onto the carbon in order to make the carbon negatively charged. Okay. In my previous video, of which I will place the link in the description section, I have explained into details, vividly, the secrets behind these arrows. Okay. Why the base is taking the proton and why the proton is also donating its electron onto the carbon to make the carbon negatively charged. Alright, so if you are confused at this stage, I would advise you to go back, go and watch that video and come back to the content. Trust me, you will understand. It's very simple. Alright, now that we have established this fact, okay, then it means that we have now formed our carbanion, right? So now the transformation is going to look like this. Yes, so it's going to look like this is the product that I'm going to get. This is what is going to be my carbanion. Alright. Why? Because now I have a negative charge on this particular carbon. Because that was where I abstracted the proton. Okay. Now the next thing to do is to balance or stabilize our carbanion through what? Resonance. Okay. Anytime you undergo a carbonyl condensation reaction, whether aldol reaction and the other reactions, anytime you form a carbanion, do not forget to stabilize the carbanion through what? Resonance. Alright. Now, with resonance, I'm going to introduce the resonance arrow, which is a double-headed arrow. Anytime you see this arrow, it tells you that it's a resonance system. Okay. Now, with resonance, what is going to happen? The electron here that is located on this carbon is going to be transferred to be shared in between these 2 carbons. Alright. And to prevent carbon, which is this carbon, from having more than 4 bonds, we end up breaking the pi bond onto the oxygen. Alright, so you remember in chemistry, anytime you are forming a new bond around a carbon atom, make sure you remember to break one. If not, you end up violating the rule that carbon must not have more than 4 bonds. Alright, the maximum number of bonds carbon can form is 4. Right, so anytime you are forming a new bond with a carbon, make sure you are mindful of the number of bonds that are present around it. Okay. So because of that, that is why when we transfer this electron to be shared in between these 2 carbon atoms, we decided to bring the pi bond onto the oxygen, right? To swerve carbon from what? Having more than 4 bonds, alright? Good. Now that we have our resonance occurring, what is going to be our final structure or our resonance counterpart? Yes, so this is how our resonance counterpart is going to look like. After we have done the transformation, the movement of the electrons throughout the system, this is what we end up getting. Okay, and this is what we call enolate ion. Okay, this is what we call enolate ion. Whilst this is what we call carbon ion. Alright, and these two are referred to as what? Resonance pairs. Okay, good. Now that we have established our resonance system, we are sure now that our carbon ion is stabilized. Okay, now what happens next? The next step in this reaction is the interaction, okay, or the reaction between the two carbonyl systems. All right, one of the carbonyls in this system now is going to act as a nucleophilic donor, okay, whilst the other one serves as an electrophilic acceptor. If I say a nucleophilic donor, it means that within the system, the carbonyl system, or the part that is negatively charged, the part that is having electrons to donate, okay. And then if I talk about electrophilic acceptor, it means that the part that is what? Lacking electrons and is willing to what? Accept electrons. Okay. Now, in order to proceed, you can decide to work with the carbon ion, or you can decide to work with the enolate ion. It's your choice. So you can pick whichever one you want to pick. It's simple to work with any of them, alright? But for the purpose of this video, I'm going to use the carbon ion. Okay. Alright. Let me write it here for you to see it clearly. Yeah. So now we have our carbon ion here. Okay. I just picked the carbon ion from the resonance system, right? Good. Now, as I said, we need the carbonyl systems to react or interact with each other, okay, so that we can end up forming our cyclic product. Okay. Now, this part of the structure, this carbonyl system is what is serving as the nucleophilic donor, and this part is what is serving as the electrophilic acceptor. Okay. Now, what is going to happen is that our carbon ion, or the carbon bearing the negative charge, okay, will attack the carbonyl carbon or the second or the next carbonyl system. Okay. Do not make a mistake. This carbon ion cannot come back to attack this carbon. Why? Because this carbon ion was formed with respect to this carbonyl system, so it cannot attack itself. Okay, it's like if you want to kill someone, you don't go and kill your own family members, you go outside to kill. Do you get it? Yes. So this carbon ion here, this negative charge, cannot attack its own carbonyl carbon. Rather, it has to go outside to attack the nearest possible carbonyl system, which is this one. Do you get it? Good. Now, to show the attack, I'm just going to draw the arrow directly to the carbonyl carbon. Okay. So it tells me that this carbon, okay, is acting as a nucleophilic donor, and it is attacking what? This carbonyl system. Okay. Now, why is this carbon acting as an electrophilic acceptor? Okay. In my previous video again, I explained this using polarization. Okay. Polarization of bonds, in a sense that because oxygen is more electronegative than this carbon, it ends up polarizing the bond, and then electrons get pulled towards oxygen more than what carbon. So this carbon becomes partially positively charged, whilst the oxygen here becomes partially negatively charged. Okay, so because of that, this negative charge have gotten that opportunity to interact with it. Do you get it? Right. Now, because of your explanation, or for the purpose of your understanding, that was why I wrote it, but then it's not really necessary for you to write the partial charges on it. Okay. Now, you just have to bear it in mind that that is what is actually happening. Okay, that is the main reason why the negative charge is attacking the carbon in here. Okay, good. And as I said earlier on, anytime you are forming a new bond around carbon, make sure you break another one to prevent carbon from having more than 4 bonds. Okay, so because this carbon is going to be bonding with this carbonyl carbon, we need to break what? The pi bond onto the oxygen. Do you get it? Now, once you do that, you end up forming a cyclic structure. Okay. Now, how do you know the size of your cyclic structure, or how do you know the type of cyclic structure you are forming? Okay. All you have to do is count the number of carbon atoms within the ring that you have formed. Okay. A ring can be anything. So far as there is no opening, it is a ring. Okay. This can be a ring. 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 So far as it has no open end, it is a ring. Okay. Cool. So now let's look at this. Now this is a ring because you could see that this carbon is connected to this carbon. So this whole system is now enclosed. Alright, so it becomes a ring. Okay. Now you have to just count the number of carbons within your ring. Then you determine the number of or the size of your cyclic structure. Now let's count together. We have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 in our ring. This particular carbon is not part of the ring. Why? Because the ring is ending on this carbon and this is just a substituent attached to it. Okay, so this particular carbon is not part of our ring. Okay, good. Now that we have realized that, okay, the number of carbons in the system or in our ring is 6, then what is the simplest polygon that has 6 sides or 6 carbons within it? It is what? A hexagon, right? So you just come and draw hexagon here directly without wasting time. Okay, now after drawing your hexagon, you can decide to name the number of carbons within it so that anytime you want to add the substituents to it, it will be simple and easy for you. Okay, you can name it from anywhere, there is no specific restriction. All right, so I decide to label here as my carbon 1 and I decide to label here as my carbon 6. Okay, which means automatically here will be 2, 3, 4, and 5. You can decide to name anyhow. Okay, good. So after labeling your ring structure, okay, all you have to do is come back to your original structure, okay, and then try to transfer every substituent on it to their respective positions on the ring. Okay, so if I check carbon 1, what do I have? The carbon 1 has no substituents. Okay, carbon 2, what do I have? I have what? Double bond oxygen attached to it. Alright, so I'm just going to put double bond oxygen attached to my carbon 2. Carbon 3, there is nothing. Carbon 4, there is nothing. Carbon 5, nothing. Carbon 6, okay, on my carbon 6, I have oxygen minus. Why is it a negatively charged oxygen? Because as I said, as this carbon 1 attacked, we need to break one of the bonds onto the oxygen to make oxygen negatively charged, right? And that is what is happening over here. Do you get it? And that same carbon 6 is having a substituent over here, one methyl group attached to it over here. So you just have to attach that methyl group to it. Okay. Now you've realized that you have gotten an intermediate product. This is the intermediate product or the intermediate aldol product. Okay. Now what next? If you remember, we used a base. Okay, we used a base which was a hydroxide ion. Okay, to abstract our proton from the alpha carbon. Right. Good. So doing that, we ended up having this, which in that case becomes water, right? Good. Now that base which was holding the proton will now come and donate that proton into the system. It's just like you giving money to someone to keep for you, and whenever you need the money, you go in for it. Okay. So we have given our proton to the base to hold. Okay. Now that the system needs the proton, we just abstract it or take it back from the base. All right. Good. Now let me write it clearly for you to see what I'm trying to say. Good. Now we have our intermediate aldol product here, right? And then as I said, our base is holding our proton for us. Is that not it? Now the system needs the proton back. Okay. And when you look at this structure, which of the component do you think needs the proton? It is this oxygen minus, right? So the negative charge or the negatively charged oxygen comes to pick the proton, and then the proton brings its bond onto the base. Okay. Now when that happens, we end up forming our aldol product. We end up forming an aldol product, and this is what we call the beta hydroxy molecule or compound. Okay, this is a beta hydroxy molecule or beta hydroxy compound because if you check, this is a carbonyl system, okay, and then this carbon is alpha to this carbon, right? This carbon is alpha to the carbonyl system, and this carbon is beta to the carbonyl system, right? So because the hydroxyl group or the alcohol group is present on the beta carbon, That's why I say it is beta hydroxy. Alright. Now ask yourself, would this particular product be able to proceed to form a condensation product? Okay, in my previous video I explained how aldol condensation products are formed. Okay, now when you subject this aldol product to heat, okay, there is a possibility that water can be taken out of the system, and when that happens you end up forming an enone, okay, an aldol condensation product. All right. Now, before you identify that, you need to be able to identify certain key factors or key things about your molecule before you decide as to whether it will be able to proceed to go through the condensation reaction. Okay. Now, the first thing that you need to look at is you check the alpha carbon that is in between the two functional groups. Okay. This is the ketone functional group. This is the alcohol functional group, and then the alpha carbon between the two of them is this carbon. This carbon. Now you need to find out if that carbon has hydrogens on it. Okay, so you realize that this carbon, because it doesn't have any substituent, automatically to have what? 2 hydrogens attached to it. If it had 2 substituents, it means that there will be no hydrogens attached to them. Okay, so far as you are able to get hydrogens attached to it, then it means that this particular molecule can proceed, okay, to go through the condensation reaction process. All right. Now let's look at how that occurs. Good. Now this is our aldol product, and if I subject it to heat, okay, I expect to remove water from it, and we know water is made up of hydroxyl group and then a proton. Okay. Now we have a hydroxyl group here. We are going to take it off. In addition to one of the protons in here. Okay, once we do that, we end up establishing a double bond within the system. Okay, now our final product will end up looking this way. Our final product will look like this, and this is what we call the enone molecule. This is our aldol condensation product. All right, good. If you're able to follow this very carefully, I am sure by now you have gotten the understanding of how the mechanism of aldol condensation and intramolecular aldol reaction works. Okay, and then if you find out or you meet such a question anywhere, you'll be able to find your way around it. All right, good. There is one thing that I want to touch on before I bring this presentation to an end. Okay, now when you are dealing with intramolecular aldol reactions, okay, there are several ring structures that can be formed. Okay, we can form 3 members, 4 membered, 5 membered, 6 membered, 7, 8, 9, 10 membered rings. Okay, so far as you are dealing with intramolecular aldol reaction, which involves the formation of a cyclic product, you end up forming different sizes of rings. Okay, now sometimes they might ask you to identify the most stable products. Okay, now the stability of your product is dependent on the size of your ring. Okay, now just keep this in mind. Anytime you form a 6-membered ring, that becomes the most stable product. Okay, the 6-membered rings are usually the most stable products, followed by the 5th or the 5-membered rings before you go to your 7, 8, 9, 10. Okay, so usually the formation of cyclic product favors 6-membered rings, followed by 5, 7, then you continue like that. Okay, the 3 and the 4-membered rings are also possible. You can also form them, just that aldol reactions don't usually favor their formation, but then it is also possible. Okay, and anytime you form them, in addition to any of these rings, you know which one becomes more stable. Okay, based on what I just said earlier on. Okay, now for example, if you are being given a system that requires that you form 2 products, okay, and then in a situation where one of them is a 6-membered ring and then the other becomes a 4-membered ring, what do you think will happen? Which of them become the major product, or which of them is the most stable product? Obviously, as I said earlier on, the 6-membered ring will be the most stable product in between the 2. So if you are considering 6 and 4, the 6 becomes the most stable. If you are considering 5 and 7, 5 becomes the most stable. If you are considering 5 and 4, 5 becomes the most stable. Please, are you good? Great. I am so grateful that you've been able to stay with me from the beginning till now, and I am sure by now you've gotten something positive out of this, and it has helped to improve your understanding. Thank you very much, and I will see you in the next video.